Continuing on here with our discussion of the limitations of buffers, we're going to talk about buffer capacity and buffer range. So the more acid and base that is used to prepare a buffer, the more acid base it can neutralize. It's going to have what we call a greater capacity. So the more stuff you use, the more stuff you can neutralize. And this should make logical sense. The whole point of the buffer is that we have a whole bunch of these molecules that are essentially sacrificing themselves so that the pH doesn't change. Well, the more you have of those, the more it can handle. If you have very, very few of those, well, the buffer is going to get overwhelmed really easily. The pH range is the range of the pH values over which a buffer system works effectively. What we mean by this is if you want to buffer a solution at a pH of, let's say, 4, you probably don't want to pick ammonia as your base, as your building block essentially for your buffering system, because that wants to buffer in the basic range, not in the acidic range. So each individual buffering system, which is to say each individual conjugate acid-base pair, work in certain pH ranges and really don't work in other pH ranges. So we have to pick the acid-base pair that we want by looking at the pKa of the acid in the pair. We want to choose the acid with the pKa that is closest to the desired pH. Because when we have those as close as possible, the ratio between the acid and base is as close to 1 as possible. As we vary away from the pKa of the acid, we have to start messing with the ratio in the Henderson-Hasselbalch to get the pH to work out correctly. So if you remember, the Henderson-Hasselbalch looks like this. If you're familiar with log math, if the concentration of base and acid are the same, we would just have 1 here, and the log of 1 is just 0. So if you have an exactly equal ratio here, exactly equal to 1 ratio here, then the pH of your buffer is going to be the same as the pKa. So as you vary away from the value of the pKa to get a pH that is different than the pKa, you have to mess with this ratio. So you either have to have more base and less acid, or more acid and less base, just depending on which direction you're trying to shift the pH. And as you do that, the buffer becomes less effective. So in the extreme cases, where you're really pushing that ratio to one side or the other, the buffer's just not going to work well at all. It'll still be better than nothing, but it's not going to work nearly as well as it should. Alright. So this is kind of reiterating what we're just talking about. Buffers work best when that ratio of concentrations is very close to 1. When the desired pH is far from the pKa, you have to significantly vary one concentration from the other to get the pH that you want. Alright. And it says here, this causes the buffer to not work well in one direction. It really doesn't work well in either direction, but it works a lot worse in one than the other. If you push the ratio even farther away with that buffer, then you get a larger change in the pH than if you go back closer to the ratio of 1 to 1. But in either direction, it doesn't work very well. So let's look at a couple examples here. So this is kind of a busy slide, but hopefully I can parse it out for you. So we have 2 buffered solutions in both of our examples here, and we're using the exact same acid in all 4 of these example solutions. So we have 1, 2, 3, and 4. We have 4 different solutions here, but we're going to be comparing 1 and 2 and 3 and 4. There's not really a use for comparing between the two pairs here. So if we compare solutions 1 and solutions 2, or buffer 1 and buffer 2, if we look at what we have to begin with, over here we start with point 1 and point 1 of our acid and base, and we add 0.01 moles of base. Over here, we didn't want an initial pH of 5. So we're still using, again, the exact same buffer system. It's the same molecules, but instead of trying to buffer at 5, which is the pKa of this acid, we wanted to buffer at 4.05. So right at the edge of what would be useful for this buffer, because we don't want to buffer beyond 1 unit away from the pKa. So we're right at the edge of what would be acceptable for us. And so to get the pH to that level, we had to mess with this ratio. The total number of molecules here is still the same. So we had 0.2 moles of acid and base over here, and we still just have 0.2 moles over here. But we had to mess with the ratio so that we have 0.18 as acid and 0.02 as the base to get this pH for our initial pH. We still add the exact same amount of base, and as you can see, it held up pretty well, actually. So the base here that we added did change the pH to 4.25, so we had a change of 0.2, which is a 5% change, which is, all told, is not terrible. Like, it was a buffer, and it did buffer the system, and it helped quite a bit. But because it was right at the outer edge of its usefulness, we had a 5% change versus only a 1.8% change over here. So we had less than half of the change in this buffer, where it was buffered close, or not close, it was buffered exactly at the pKa. So I'm not saying that the buffer doesn't work if it's right out there at the edge of what we would accept, but it doesn't work as well. Similarly, down here in examples 3 and 4, we again have the exact same acid, and in this case, we're going to have the same ratio even for both of these. We have half a mole and half a mole on the left, but we have 0.05 and 0.05 moles in the second or the fourth solution here. So in both cases, we're starting at a pH of 5. We're starting with an even ratio. But because this solution has so much more, so many more molecules, the buffer has a higher capacity. It's better able to handle the addition of 0.01 moles of a base, so that you only get 0.4% change. I mean, that's almost undetectable, depending on what instruments you're using. Like with our stuff we use in the lab, I think we can get down to 100ths of a pH unit, but I'm not even 100% sure that we can. It might even just be tenths, but I think it's 100ths. So that is right at the edge of just being able to detect with our lab equipment. Whereas this one, that had 1/10 the capacity, again, it still didn't change dramatically, but it changed a whole lot more than this one did. So we had a change from 5 to 5.18. So a 3.5% change versus a less than a 0.5% change. So the range and the capacity of a buffer are really important things that we need to take into account when we're deciding what kind of buffer is going to use, deciding how strong or how high a capacity a buffer we want to make. We have to take these things into account. So, like I said, most of the time, when we're going to be looking at this and we're going to be doing this kind of chemistry, you're not actually going to be calculating the pH of a buffer. If you're going to be a biochemist, if you're someone that is taking this class on the road to a biochemistry degree, most of the time it's not going to be a situation where we have this solution and we're like, oh, I'm curious as to what the pH is. Now, most of the time, if you're curious about the pH, you're just going to stick a pH meter in it, in the solution, and find out what it is. Instead, mostly what you're going to be doing is preparing a buffer. So you will know the buffer that you need, or know the pH that you need, and then it will be your job to make that buffer. So you'll need to calculate the concentrations of acids and salts, and pick the best acid and salt for the job. So with that in mind, which acid would you choose to combine with its sodium salt to make a solution buffered at a pH of 4.25? For the best choice, calculate the ratio of the conjugate base to acid required to attain the desired pH. So we want a pH of 4.25, and we have these choices. So go ahead and pause the video, pick the acid that is the best acid to use to make this buffer, and then try to find the ratio. So we're trying to find this. You don't need to work out what those two numbers are. If we had a total concentration to start with, we could actually find those, or if we just randomly picked the capacity that we wanted, we could find those, but we're not going to do that here. We're just going to find the ratio. So go ahead and pause the video and try to find that. Alright, hopefully you decided this one, the formic acid, was the best acid to use to make our buffer. The reason for that is it is the closest to the desired pH. Technically, we could have used nitrous acid as well. That would have worked because it's within 1. Remember what I said earlier, that we want to be within 1 unit of the, let me rephrase that. We want our pKa value to be within 1 unit of the pH that we want. And so either of those are within 1 of 4.25, but neither chlorous acid nor hypochlorous acid are within 1. They're all well over 2 or even 3 away. So we're going to go with the formic acid. We know we want a pH of 4.25, and we know that the pKa for formic acid is 3.74. So what we want to do is solve for this ratio. So again, this is the Henderson-Hasselbalch here. It's the equation I have written out here. We have the pH, which was given in the problem, 4.25, is equal to the pKa. Again, we picked that pKa out of the list, plus the log of the base over the acid, and that ratio is what we're trying to find. So if we solve for that ratio, what we will do is we'll have 4.25 minus 3.74, and then we're going to take the anti-log of the 0.51 that we get there, which is to say we're going to take 10 raised to 0.51. And that gives us, for our ratio, 3.24. So with that ratio then, we could essentially pick the capacity we wanted. So if we wanted to have a really high capacity buffer that could withstand a brutal beating from either acid or base that we throw in there, we could have 3.24 molar base and 1 molar acid. Now, that would definitely be an overpowered buffer, and I don't even know if you would, like, that's kind of ridiculous to have that much material in there. But it's possible, and that would give you the ratio that you would want to have that pH. But realistically, you would probably maybe move the decimal point over 1, and maybe have 0.324 and 0.1, and that would still give you the ratio you want. But any values there that give you that 3.24 ratio will give you the pH that you're looking for. All right, call it there for this video. In the next video, we're going to talk about the last, mercifully, the last topic of Chapter 14, which, not mercifully, is one of the longer topics. I know it seems like Chapter 14 has gone on forever, but titration is the last topic, so once we get through that, we will be done with Chapter 14. So I'll see you in the next video to talk about titrations.